Good afternoon, everyone, and welcome to today's webinar. This is a webinar organized by Flow Batteries Europe, Scaling Flow Batteries Strategies, Trends, and Paths to Grid Scale Impacts. The slides will be shared after the meeting, as always, and we will have 3 presentations followed by panel discussion where we will take questions. For these questions, please use the Q&A feature. So Flow Batteries Europe is the leading flow battery trade association representing the flow battery industry in Europe and globally. So we're a members-led organization with membership covering the full battery value chain, both in Europe and around the world, where we are aiming to shape the legal regulatory framework around flow batteries at the European level and influence and contribute to decision-making to contribute a more friendly environment for long-duration energy storage and flow batteries. Next, please. Here you can see our members. So Flow Batteries Europe now has 31 members across the value chain and around the world, where we're working together to improve the regulatory environments for flow batteries. And we'd be very happy for anyone interested here to join us. And we are joined by 3 of our members here today who will give presentations on flow battery scale-up. Today's webinar is moderated by Secretary General Anthony Price, who I'll hand over to now.
Good afternoon. We know that reliable, large-scale, low-cost energy storage is a key requirement for most power systems. We need electricity storage to maintain the balance between generation and demand, whether for short-time intervals or long-time intervals. In our previous webinars, we've talked about how flow batteries are being used for electricity storage on today's power networks and the emerging applications for providing reliable support for data centers. Today, we're continuing that theme by looking at how manufacturers will scale up their manufacturing and production to meet this extra demand. I'm Anthony Price. I'm Secretary General of Flow Batteries Europe, and I'm also a program coordinator for the International Flow Battery Forum, which meets again this year in Budapest in Hungary in June. The call for proposals is still open, and if you've got some ideas of presentations, posters, or sessions that you would like to join in, please submit your proposals soon. In fact, the call closes on Sunday, so now's a good time to get writing on that. What we're going to be doing is introducing 3 leading names from the flow battery industry to help us understand the potential for large-scale production, which is, of course, a prerequisite to achieving large-scale growth in this sector. We'll be covering designs, considerations for scaling flow batteries, challenges and solutions for cost-effective expansion, case studies of successful large-scale installations, innovations in materials and system management for enhanced performance. So first of all, let me welcome Nathan Ball from Quino Energy. Quino's a company based in California that's been working in the organic flow battery sector. Over to Nathan for a short 10-minute talk. Thank you.
You're still muted.
Okay, thank you. So thanks, Anthony, for inviting me to share some insights and opinions about the growth of the flow battery market and the potential for flow batteries to reach large industrial scale that will bring huge benefits for utilities in the global community. My name is Nathan Ball, and simply stated, as you can see on this slide here, in the battery industry, cost innovation increases the size of the market, and increasing the size of the market further reduces battery costs. If you look back in just 5 years, there were less than 5 gigawatt hours of utility BESS installed. And looking 5 years into the future, we're now expecting 100 times that amount. Notably, Europe is a fast-growing market for utility batteries. The business and public policy decisions that you're making now in Europe will have a big impact on our industry. Installation costs have fallen dramatically from almost $600 per kilowatt hour in 2017 to less than $200 in 2025. Our strategy to commercialize new technology is to partner with flow battery manufacturers around the world who are already producing at scale to commercialize new innovations, and we see many exciting innovations from ourselves and others that can push flow battery costs and market growth in an exponential path. So next slide. Compared to other energy storage technologies, proven flow battery benefits include long lifetime, safety permitting, and sustainability. Their drawbacks until now have been relatively lower energy density and higher cost compared to lithium ion for most applications. But there's a lot of innovation happening to improve both energy density and cost for flow batteries. For example, there's a BESS project in Switzerland that will be built underground, and the containers will likely be stacked several units high. Lithium-ion batteries cannot do this because of the fire hazard regulations. Future large-scale installations will also store electrolytes, which exist as fluids in large tanks built in place, so that a future flow battery installation may not look like a battery as we know it today, but more like a water treatment plant or a fuel storage facility. Innovations that will reduce costs include advanced electrolyte system architecture, manufacturing and installation efficiencies, and all are needed. Next slide. Just looking at the three companies on this call, each has demonstrated a number of innovations that are reducing flow battery project costs as larger and larger projects are built. For example, on the bottom left here, you can see a delivery of organic electrolyte from Quino Energy. This electrolyte works as a replacement for vanadium electrolyte in flow batteries and has the potential to reduce electrolyte costs by up to 75%. As you can see on the left pie chart, electrolyte is the largest cost component of flow batteries today. In the bottom middle picture, you see Yena flow batteries and Suqian Time energy storage's stack technology. Together with more innovations that they have, also in tanks and balance of plant and other components, these companies have shown significant improvements in both battery system performance efficiency and manufacturability. On the bottom right, you see an example from Invinity of a mechanical foundation from their recent Endurium installation, which is a big improvement over large poured concrete foundations that were a feature of earlier flow batteries, significantly speeding up the time to install and reducing the cost. In Quino Energy's view, with a combination of innovations like these, flow batteries will achieve at or below cost parity with any other energy storage technology for many applications when you put the pieces together. And we have detailed cost models that we've been collaborating on with utilities and other partners, both in the EU and in the US, to substantiate this claim. Next slide. Quino Energy is an electrolyte manufacturer, and we partner with flow battery OEMs to pilot and commercialize organic flow battery technology. This technology spun out of Harvard in 2022 based on fundamental breakthroughs in organic electrolyte performance and methods to manufacture it. We have a ton-scale electrolyte pilot production plant in Buffalo, New York today, and with the close of our Series A financing in November of last year, we are now building the first industrial manufacturing capacity in India. One of the unique benefits of our organic electrolyte is the ease of manufacturing with abundant raw materials and a zero-waste process that can be operated anywhere in the world. Quino Energy has partners in the US and EU that are also ready to manufacture electrolyte according to our regional supply chain strategy. As we scale the electrolyte production process, you can see on the bottom half of this slide, we've also demonstrated larger and larger organic flow battery systems using commercial hardware provided by others. In this way, Quino can rely on the expertise and existing manufacturing capacity of our partners who already manufacture flow batteries at scale to bring new technology quickly to that commercial scale. We are excited also to announce, shown on the bottom right-hand corner, our first megawatt-hour scale pilot in Southern California this year, and more projects announcements will follow soon. Next slide. In a bit more detail, the Los Angeles County project in California will integrate an existing 1 megawatt solar supply, seen here on these parking structure rooftops, with Quino's organic flow battery as a microgrid to power this healthcare center. The microgrid will add energy resiliency to the healthcare center, improve their sustainability profile by eliminating solar curtailment, and reduce their electricity costs by more than $200,000 per year. We and our partners are very excited about this project. The contract is signed. The start date is February 1st, and construction will begin later this year. Next slide. In summary, scale is enabled by innovation. Quino, Jena, and Invinity, and many others are innovating rapidly in the flow battery industry. And Quino has a partnership strategy to scale globally so that we can leverage the manufacturing capacity and expertise of others. Thank you very much for inviting me again. I look forward to seeing more exciting innovations in flow battery projects from both Jena and Invinity later in the presentation.
Thank you very much, Nathan. Our next speaker is Tobias Janaszka, who's CTO of Yena Flow Batteries. Yena Flow Batteries has built the world's largest aqueous organic flow battery energy storage system in orders in Mongolia. So he'll be talking about how they've gone from laboratory validation to full-scale flow battery deployment. Over to you, Tobias.
Well, thank you very much for your kind introduction, and for the opportunity to speak today, and for your kind invitation. I'm with a company called Yena Flow Batteries, or we've been known as Yena Batteries in the past. We've been in the field of developing organic metal-free flow batteries for about 10 years now, have established significant know-how in that field, starting out at the very small level in the laboratory, and recently, together with our new majority shareholder, Time Energy Storage from China, scaled the technology to megawatt hour applications. Our partner, Time Energy Storage, stands out as one of the few companies that have integrated the entire value chain for everything that's needed to build flow batteries, as we will see throughout this presentation. And I believe this is the fundamental basis for scaling the technology in the future. And bringing in the know-how on the fundamental properties of the materials, combining that with the manufacturing expertise, I think we have a proper strategic synergy in place that will enable organic and metal-free flow batteries to grow in the near future. Next slide, please. Nathan already introduced the idea of using organic materials, and I think it's quite reasonable to do that and work with organic materials for a very simple reason. It's the most abundant elements that are available out there. Carbon, nitrogen, oxygen are needed to make these materials, and therefore they can be produced in a large scale at low cost without raw materials constraints. Next slide, please. But when scaling such materials, the very big initial question is where to start. Basically, what kind of materials to use, what kind of molecules to build. All flow batteries work by very much the same principle, having two tanks, having stacks, and so on. But what you fill into the tank really matters. And with millions and millions of combinations of carbon, nitrogen, hydrogen, and all of these elements out there, the challenge really lies in finding the right molecules, finding something that can be produced on low cost and large scale, that has high energy density, that is stable over long periods of time. So initially, we focused, of course, on finding the right material combinations. Next slide, please. This is something done in the laboratory at very small scale. You start with grams, milligrams of materials, do molecular screenings, compatibility screenings, and so on. The next step when talking about scaling flow batteries is to go for laboratory pilots. Therefore, you need maybe 10 kilograms of material, which is already somewhat challenging. However, the really exciting part only starts afterwards, and that's the part when the real technology development and the whole engineering starts. You know, as a chemist, I always said, well, we do the chemistry, that's the difficult thing. But later on, I had to realize that the engineering is actually as challenging, or maybe even more challenging. And when you start engineering and building first pilots, of course, things are to some degree still simple. You build a one of a kind device and make sure that it works. The first time we did that was the world's first organic flow battery that was put into field application in 2019 within the Energy Keeper project. And for such a device, of course, scaling material was a key challenge for us. Going from 10 kilograms to thousands of kilograms or ton scale not only brought along challenges in terms of sourcing that material, but it's of course the first time a company and a startup company has to deal with a lot of regulatory issues. So that's the first time when European REACH regulation, chemical regulation kicks in, when topics like water protection laws, when topics like safety and so on need to be scaled and handled. Nice thing is you can easily do that with flow batteries, but it's something you need to keep in mind and something one really needs to start working on early. Of course, going from that scale and having proven that a certain combination of materials, a certain new chemistry is working, brings us to the next step. Next slide, please. Which is translating the knowledge gained by such pilot systems into actual product development and standardized system architectures. I think we will hear throughout this webinar much more about that, but I believe, yeah, it's really a crucial step because here, when you're going for this, one has to decide not only on the materials and the components, but also on how and where to source of these components, how to establish an industrial grade quality documentation and certification framework, how to balance actually the whole supply chain. And as a startup company, several years ago, we relied heavily on the buy part of the make and buy decision, basically because smaller companies have challenges integrating everything that's needed to make a flow battery. But over the last 2-3 years, together with our partner from Suchen, we learned that it really comes as an advantage to have the capability to actually go for the make part of this decision, because it really speeds up things to have major component manufacturing in-house. Next slide, please. And based on that, of course, one has to decide what kinds of components to manufacture. Will I only go for a defined type of flow battery in the end, or do I want to have a platform kind of technology? Do I go for the stack, or do I go and for the electrolyte, or do I even go for key raw materials that go inside the stack? Do I span that even all the way to auxiliary materials like tanks and tubes and so on? Do I even go for maybe pipes and electronic chips for the BMS? What's about the programming of the control system? So all of these questions need to be sorted out. And we basically came to a decision that an integrated platform that can serve several chemistries, metal flow batteries like organic flow batteries, vanadium flow batteries, and other, is the right way to go. And next slide, please. And for that, key integration of major parts has been established. For these major parts, of course, the stack is one of the important power and performance defining components besides the electrolyte. And therefore, bipolar plate manufacturing, felt manufacturing, so electrode manufacturing was established. And with this deep integration, we really have now the capability of adapting very quickly the materials to the needs of new molecules and adapted recipes of the electrolyte. Next slide, please. The same holds true for a component inside the stack that separates the anolyte and the catholyte. A special property of many organic metal-free chemistries is that there's two different materials used for the pozolite and the nicholite, so the two terminals of the battery. So it's strategic to have a great membrane material that separates these two, because this membrane material will define not only performance but also long-term durability and lifetime of the battery. We have established membrane manufacturing for about 2 gigawatt of stack capacity per year, and have found a material that perfectly fits the chemistry we are using. Next slide, please. Of course, all of these components need to be integrated into cell stacks. For that, plastic, not only the cell stack design needs to be carried out. We decided to have that in-house, but of course there's also other flow battery manufacturers and dedicated stack manufacturers out there that are also developing stack designs. We decided to do that fitting our chemistry, and basically scaled the plastic handling, the injection molding, all of that that's needed to make frames in key parts of the stack, but also integrating the manufacturing by stepwise going through automated processing, because we believe it's important to have that in hand in order to manufacture at good quality and large scale. Next slide, please. Having already all of that plastic handling, it's actually quite logical to also make the plastic tanks in-house and then fit them into the tanks, into the containers for shipping purposes and so on. This really allows full control over quality and stability and sturdiness of the systems. And we actually noticed that with commercial parts, there's certain additives and so on that can be challenging. Next slides, please. In the end, all of these components need to be integrated with the electrolyte, which we do have partners within the group of companies we're working with that have scaled that up to the 10,000 ton scale. Next slide, please. And basically then finally integrating all of these components into the flow battery containers. Here you can see a set of containers that is being made ready for shipping, and that was, next slide, integrated in what's now the world's largest organic flow battery system, a 20 megawatt hour flow battery system that was put into operation in northern China, in Mongolia, summer last year, and really shows that the technology is ready and can be, and was scaled and could easily be scaled from laboratory all the way to large scale field application. This is now the basis for future projects to come. Next slide, please. That are now mainly based on standardized container-based products. Based on that, we can, and that's the advantage of having the whole value chain at hand, offer OEM components to partner companies, and having membrane manufacturing and stack know-how in-house also allows, based on the scaling of the flow batteries, to diversify the portfolio and go for other products that require stacks like electrolysis systems. With that, I would like to close. Thank you very much and hand over to Anthony again.
Thank you very much, Tobias. That was great, very informative, and thank you for your insight into how you're bringing the skills of all your resources in-house in order to reach scale. We're now going to welcome Jean-Louis Cole from Invinity Energy Systems. Invinity is a company well known to many of us. Over the years, they've brought together many companies working in vanadium flow batteries. So Jean-Louis is going to be giving us his views on increasing project size and how to grow the VFB value chain. Over to you, Jean-Louis.
Thank you, Anthony. I'm going to try and share what we've learned putting together large projects in a megawatt hour scale. And we've not done it once, we've done it in many different geographies to support the grid and trade energy at utility scale. So what we've learned is a lot, and I'm going to be quite brief on this presentation, but we've learned a lot, and that's really humbly what I'm trying to share today. Is that when you prepare to go to infrastructure scale projects to support the grids around the world that are loaded with more renewables, you need to be ready, and that's really my message. How do we get ready for these infrastructure projects? You can see that we've got projects from California, the UK, several places in Europe, all the way to Asia, and last but not least, Spencer Energy in Southern Australia. These projects in the last 3 years have delivered to the grid 7.7 gigawatt hours of energy. So they're running day in, day out. That's what we're learning, how to do this. Next slide, please. We started with commercial and industrial projects, in the 1 megawatt hour scale, few containers, in the UK, in America, in Belgium, a few examples there. But really the one that blew our minds back in 2021, it's been operating since 2022, but we built it, designed it and built it in 2021, was the Energy Super Hub Oxford in England. And that's 5 megawatt hour. Looks very, very small, but at the time it was really huge for us. 27 20-foot containers. That's 162 flow battery modules, with the 2 tanks and the stacks and the pumps and everything, 162 of them running together, connected to a utility grade inverter and connected to the national grid of the UK. This was really a very steep learning curve. And then we did it again. We did the 8 megawatt hours in Australia. And that one is DC coupled with a large field of solar panels. And we did the same very similar architecture in Canada, in Alberta. This 10 megawatt hour system in the USA for a casino resort, which is more kind of a commercial industrial, but at that scale, 10 megawatt hours, where they want to be able to be independent from the grid. If the grid falls, they'll be able to run on the batteries. And the one that we are currently building, you've seen probably videos of the containers being installed, 20.7 megawatt hours in the UK under the LODIS scheme. And this project has the particularity that Invinity owns the project, is acting both as the project developer and the OEM. And we are learning. We have learned how to go through the process of putting together the business case and delivering a project for an infrastructure on the national grid in real conditions. So you can see the scale goes up. Next slide. I was talking about scores of megawatt hours, but this is more. The needs of the market are huge. So where does this lead us? Well, in the UK cap and floor scheme, under that scheme, we have engaged with project developers and many of these projects, 21 of them, were deemed acceptable under the UK cap and floor scheme. If you total them, it's 16.7 gigawatt hours project. Each project has a minimum size 400. So we are already committed to the hundreds of megawatt hour scale on infrastructure projects. Then you see what's happening around the world. In China, Ronke, kudos to them, have put together a 1 gigawatt hour system. And we've seen that picture in the press. And we all heard about the FlexBase project that is going to be 2 gigawatt hours. And that one is coupled to 2 things, a data center and the Star Laufenburg, which is where the 3 grids of Germany, France, and Switzerland are meeting. So that's where we're going, the gigawatt hours. Next slide, please. Well, how do you think about that? A few years ago, we were in the lab with mini cells running small batteries and see how they work, in our case, the vanadium ions are capable of catching an electron and keeping it and giving it back. How do you scale? Well, we learned from other industries. This is not just about a scientific experiment. This is about the entire value chain. And to scale, the entire value chain from mining all the way to energy trading needs to be coherent and scaled together. So you can start from the bottom of that value chain with the supply chain. We're talking about securing vanadium first and electrolyte and the materials for the stacks and putting the stacks together at industrial scale. So bulk production of chemicals, bulk production of materials, automated production lines for cells and stacks. That's how you scale at that level. Then the product. Well, if you look at our product that we're going to use in the cap and floor projects, we call it Endurium. It's a 340 kilowatt hour module. The modules that we were delivering even last year are 36 kilowatt hours each. So already the scale of a single flow battery has gone almost tenfold. So the product goes up, the cost goes down. You know, we know where lithium is, we know where the competition is, we know, but most importantly, we know the cost levels that we need to achieve such that the projects based on flow batteries are economically viable. And not only CapEx, OpEx is as important. So these products need to be engineered such that they're easy to operate, easy to maintain. And all the way up into the project world of project development, integration with the EMSs, with the PCSs, and the system integration partners. You know, how you put together hundreds of containers on the field for hundreds of megawatt hours such that everything works and is a reliable infrastructure. Last but not least, the EPCs, they learn with us how to handle our flow batteries. It's not difficult, and we make it easier again for them. I think my colleague from Quino picked on the fast installation. That's one of the things we learned. You know, how to simplify all these processes across the value chain. Next slide. The last. Right. So in summary, to us, the key is to scale in a coherent manner throughout the entire value chain. VFB profitability is established. It's a bankable technology. There are many project developers, especially in the cap and floor projects, that were able to put together business cases that work for vanadium flow batteries. We have 100 megawatt hours in installed base that we will have it this year. We are learning. We are already there. And the key is industrialization, cost optimized standard products made in series production, and partnerships with the supply chain for vanadium, for electrolyte, and for stacks and cell materials. This is how we're going to scale, by approaching that through the entire value chain. That's all I had to say.
Thank you very much, Jean-Louis, and thank you very much to all our speakers for this afternoon and for keeping to time. We now got some minutes that we can use for an open discussion and questions. I'll remind our audience that if you want to ask a question, you need to put it on the Q&A. If you put it on the chat, we won't necessarily see it. But I'm going to use my privilege as moderator to start off with the first question. Nathan, you talked about the market size, and you said that Europe was a much bigger market than America. That somewhat surprises me. I've always felt that America had been more innovative in adopting batteries, and with support through the IRA Act and various other mechanisms of local states support and support from the Department of Energy, but energy storage was powering ahead in North America. Why do you think Europe's a bigger market, please?
So maybe I can clarify. US is still a bigger market today, and it will probably still be a bigger market in 5 years' time, but Europe is growing faster. I'd say Europe is catching up. And I'm not employed in the public policy space in Europe, so maybe, you can give us some insights, but I do think that the situation is in Europe is favoring innovation in this area. It seems like.
So I think that's a very useful comment, and perhaps I misheard when you said that it's obviously the rate of change that's important, which means that really European manufacturers, or all manufacturers of storage devices, need to be ready to meet this increasing scale. You also made some comments about footprint. So here's an open question for all three of you. You talked about perhaps achieving 120 kilowatt hours per square meter, and you mentioned this could be from creating multi-stories. Could both you and perhaps Jean-Louis comment on what this really means in practice, and how footprint for energy storage could be changed dramatically by using flow batteries? Nathan first, and then Jean-Louis.
Sure. So we don't have an announced project yet, but we are working with one developer of biofuel refineries that's looking at pairing flow battery storage alongside the biofuel refineries, actually using some of these larger liquid fuel terminals as electrolyte storage tanks for a flow battery. This could make sense in places where there's a big delta between the peak energy costs and low energy costs. So just using this battery as arbitrage for an additional revenue stream for the entire refinery project. That's just one example, right? But in this case, if we're storing these liquid electrolytes in large tanks, they can be as tall as 50, 60 feet tall. I mean, that's stacking already much higher than a flow battery or than a lithium battery ever could.
Super. Jean-Louis, have you got anything to add to that, please?
Yeah. How do you think about footprint? Footprint, of course, is real estate, but it's also costs, EPC costs. So sometimes footprint is important from a real estate point of view because you don't have space. And then in that case, you can't expand horizontally, so you go vertical, right? And when you look at the projects we've done coupled with solar farms like the one in Australia, the batteries occupy a very small space of the entire land. So that's not a big issue. You're in the Australian outback okay, you've got space. It's not the problem. It's more installation costs, and we've resolved that by making it very plug and play and easy to install, simplifying everything. Now, if you really are focusing on areas where footprint is important and there's not a lot of real estate, then you go vertical. You can see on the picture that I shared from our friends from FlexBase. They're digging 25 meters deep in the ground and they're going up, right? And they're going to get, I did a quick calc, nearly to 500 megawatt hour per acre. So you do that. And the flow batteries, I would remind everyone that because they're safe, could be implemented very close to cities or in cities. And their space will be the issue. But in cities, what do? We go vertical. Look at all the tall buildings we have in our cities. So flow batteries will do the same.
Thank you very much. Can we just go on to the question of materials availability and the electrolytes and the supply chain? How do we manage to achieve this large scale of production if we're requiring to procure all our materials? Have we got enough of the basic materials in order to make enough flow batteries? Let's start with Tobias.
Well, there's a lot of different chemistries of flow batteries out there that is available, and all of them have their pros and cons. Basically, if I look at what we're doing, the organic materials, they really have the advantage of being easily sourceable. What we need is acetone and ammonia, easily available on megaton scale. So basically, what you then need is just processing plants. So the scaling is not really dependent on whether the raw materials are available or not, but it's rather a question of capital for building chemical plants, chemical factories, and the speed you can do that. So I think the key message is that there is flow battery technology that allow easy scaling. Raw material must not be a challenge or an issue. And that's why I really find it so fascinating that flow batteries basically offer a fundamental technology that has in the end the ability to use different kinds of chemistries. So even if you're going as a company for one system, one chemistry now, you might be able to switch that for another chemistry in 5 or 10 years time when there's a material that has better properties or that's lower cost or more easily to obtain.
Okay, so that's an interesting point because we've obviously heard from 2 organic flow battery manufacturers and a vanadium flow battery manufacturer. And I guess in the interests of impartiality, other flow battery chemistries are available. But could you give some comments on where we think different flow battery chemistries or technologies have their sweet spots and where they might be most useful, and where on how a developer or a project owner would choose between them? Who's going to start on this? Maybe it's Jean-Louis.
Well, I know vanadium more than everything else, of course. To the question about sourcing vanadium, well, through partnerships, that's you've seen what Immunity has announced recently. We're looking at this is the core, of course, getting access to vanadium, and vanadium is mostly the production worldwide, and there are people on the call more experts than me, so I'm not going to dwell too much on this, but most of the production is from recovering the slag from the steel mines, and this is really a good source, and there is abundance of it, so we're not worried about lacking vanadium. The more concerning part is the price of it, that, as we can see, we've seen in the past, can fluctuate depending on other market demands, like rebar for building, and we need to find a way through partnerships to be immune to these fluctuations. And the bigger the flow batteries become, the more they will have an influence on the price of vanadium, and the better we'll be able to control it. Now, other chemistries, there are other chemistries are using iron, zinc, and other things. I don't know their supply chain, but they have to think the same. Get abundant material and control the costs of it.
Okay, that's useful. Nathan.
Yeah. So I think we can look back to what happened in the lithium-ion industry as kind of a guide. There was a lot of many people today may not remember who have come to the industry more recently, but 15 years ago, there was a lot of discussion about whether silicon graphite or lithium titanate would work out as the anode in a lithium-ion battery. And on the cathode side, we're looking at different flavors of manganese, nickel, and cobalt oxides. And then there was iron phosphate. In the end, some of these chemistries have better energy density than what we're using today, which is predominantly iron phosphate. The one that won out was the chemistry that showed the lowest possible cost floor, as well as sufficiently long lifetime. Right? That's what won out in lithium ion. That's what is scaled dramatically today. And I think that's what will probably happen in the flow battery industry as well. We will still have some niche applications for these other chemistries, just like there are use cases for other types of lithium battery chemistries as well, in aviation and so forth, where they're not as cost sensitive or as lifetime sensitive, but at least in the utility space, long lifetime and low cost will win out in the end.
That's interesting. All of you have talked about the challenges of going from small scale into commercial, and then the sudden burst of joy that you realise that you've done it, you've achieved something that's large and memorable. What particular technical obstacles only emerged when you got into the field and you started producing stuff? Tobias, let's start with you and then go around all through.
Yeah, I think we have just recently been at this step. Well, I believe if you're talking about pilot installations, you are pretty much talking about a one-off installation. So it's a system where people do tests and have small number of pieces installed, and such systems allow for errors and failures. However, if you're going for commercial scale serial production, there is a huge challenge in upnumbering. A stack with 100 cells easily consists of 500 parts. So you have to find clever ways of producing this amount of parts, putting them together with everything still being fully sealed. And you need to do that at low cost and high speed. So I think the challenge really lies in upnumbering, thereby repeatability, and in the end having full control over the quality of such pretty much complex structures like a stack in the end. Of course, there's design questions, how to get the last couple of % of efficiency out of these systems. But this is all something that can be dealt with already at a pilot scale. So basically, to answer your question, I believe it's all about upnumbering and keeping quality of complex parts at a good level.
Okay, thank you. And Nathan?
Sorry, can you repeat the question?
Yeah,
Just
we were
briefly.
talking about what particular obstacles have you only found when you've gone from the first pilot scale to the first commercial scale?
Well, so you know, we're still working on our first commercial scale, going through the design phase with the engineering team on the Southern California project. But I would say that you know, really a lot of things are different when you go from pilot to commercial scale. At the pilot scale, you're mainly concerned with the battery just working, right? And so maybe some parts of the battery are over-designed. You may over-design pumps or tanks or some other sensor components. But once you really go to commercial scale, the battery has to be designed for manufacture, so that everything works efficiently and we can make the most money off of this battery possible, if that makes sense.
Okay, thank you. And Jean-Louis, you've got this interesting perspective now of both being a developer or as well as being the owner, and you've got up to a large number of large-scale installations, and you've also talked about this question of bankability and getting investor confidence. So in going from pilot to rollout, not only what technical problems have you had, but what commercial problems have you had, and how have you got over them, and are these going to be challenges still for the future?
Right. I'd say that if you look at making stacks and everything, it all boils down to one keyword: is predictability. So I think that's what is behind all our quality assurance approaches. If you want to build a business case where you bring a large number of equipment on in the field, and you are committed to operate it for 25 years, such that the rate of return is what was expected when the project was first set up, and investors recover their money and more, then you have to be predictable. So from that point, then this is really what we've been tackling, doing these projects with scores of megawatt hours in different geographies, different climates. And our first approach, putting a stack together and make sure that it works, it doesn't leak, and there are tens of thousands, hundreds of thousands of cells in those stacks that we've produced. That's a prerequisite. Other industries have resolved these problems before us in automotive, electronics, etc. Repeatability, high volume production, very rigorous quality assurance. That's the base. And I'm not even talking about that because that's a prerequisite. If you don't have that, you have nothing. It's really above that when you are developing a project that you need to know that you're going to make the revenue. So you need to integrate with, it's not technical, well, it is technical. You need to integrate with the EMSs, with the optimizers, make sure that your use cases are well known, that you know your market, that the battery is operated in an optimal manner to harvest as much revenues as possible, given what the energy market does in that region. I think, to me, that's probably the challenge, because making a battery, we solved that problem. Repeatable stacks, repeatable batteries, standard products made in factory, tested before they go to the field. Okay, that's the base of any industry. We got to do that. We've done this. Really, how do we crack the economics? And there is a learning curve there from all our partners, especially the optimizers.
Okay, so it's quite interesting that you've said about cracking the economics and making it work. I'm trying hard to look at some questions. No one's asking any questions in the questions section. I see that there's quite a lot going on in the chat, but it's difficult to monitor that. Although one comment did come up about the cost of electrolyte seems to be so significant in the cost of the flow battery, but what else could be done to significantly reduce the costs of flow batteries? Any thoughts on non-electrolyte activities which could reduce the cost? And if you've got some questions which you want answered, could you put them in the questions, please? We've got a few more minutes left. So who's going to take
Sorry,
the
Anthony,
challenge
there are questions in the Q&A. Maybe it just isn't updated, but I can read them for you if you like.
Well, maybe you ought to, because I'm not seeing them. Okay, thanks, David. Sure. Let's just take that one about what else can we do besides reducing the cost of electrolyte then. Meanwhile, I shall try and work out how to get the Q&A cut up on Teams.
Other things that the electrolyte to cut cost? Well, again, standardization, made in factory product that is repeatable, that is standard, and you crank up the volume of product, and don't hesitate to be ruthless. We know that we can make stacks with more or less cells, and gives us different power, different voltages. We can adapt, and we can change the size of the containers of the tanks, big tanks, small tanks, bigger capacity, small capacity. But all these variables are there for us as engineers, but not fall for that. Be ruthless in standardization, have the same product, factory made, increase the volumes, and then the costs are gonna go down.
Sure. Okay. Thank you. Just picking up on some questions. Yeah, I've obviously failed in my comprehension of Teams. There's a little extra button I should have pressed. One comment here about mixing together flow batteries and lithium batteries in order to gain advantages of both types. I think, Jean-Louis, you did that at the Energy Super Hub.
Yes.
Has anyone else got any experience of mixing different battery types, flow batteries with conventional? Otherwise, we'll take it from Jean-Louis.
Well, I mean, it's basically also what we have done in Mongolia. Basically, I think one can look at that from 2 points of view. And one point of view, of course, is the technical advantage of having a long duration energy storage device that is, let's say, a bit slower with the flow battery combined with a fast lithium-ion battery. But what I also think is important is to look at the potential such combinations actually offer on the long run. The question is, do we as a society want to rely on one technology alone? And the answer should probably most likely always be no. And actually starting out or maybe even mandating projects of a certain size that are being installed to combine the conventional lithium-ion batteries with other technologies to help them mature, to help them actually over this initial step into the industry, into larger scale applications, could be really beneficial. We are seeing that with some tenders already, but I think it should be employed much more often. Basically, having a battery installation in a tender, having 90% traditional battery technology, and adding 10% of new technologies, which could be flow batteries, but also other technologies, sodium batteries, whatever.
Okay, thank you very much. We've had a couple of comments and partial questions in. When do we expect flow batteries to achieve the same scale as lithium ion in terms of megawatts or megawatt hours? Couple of side comments on that. So at the moment, we certainly hear about very large lithium ion batteries commonplace being built greater than 100 megawatts. Not so necessarily sure about the megawatt hours associated with it. But 100 megawatt lithium battery doesn't really cause any waves through the industry. When will we see routinely flow batteries being built at 100 megawatts and therefore 400 megawatt hours or even gigawatt hours scale? throughout Europe. When do we think that will be? Let's go to Jean-Louis first. Then he's smiling at me.
When? Well, if you look at the market, the pool is there. Our problem is not. I've been in other industries before where you had this very nice idea, and you get a startup, and then you develop your idea, and then you try to find a market for it. We're completely the reverse. The market is pulling us. We were talking about why Europe. Well, Europe, there's certain regions of Europe where the penetration of renewables is high, and in the grid, and to stabilize the grid, you need storage. So the market's there. So when we're ready, when we go through this value chain and we make it robust from all aspects, bottom to top, like I was describing, it's an industrial process. I've in my long career, I've spent more than a decade in the mobile phone industry, and there was lithium-ion and nothing else to power those phones, and then still nothing else. But they've been working at it and improving lithium-ion batteries since the 1990s. That's where they are now. We're not going to take that long, as long. We're going to push this, looking at what other industries have done to go from pilot through projects, and then regular increase in those projects and more adoption, bankability. It's like a virtuous circle. You do more, you reduce cost, you get credibility. People see it's working, attracts more, and that's a virtuous circle that we're creating by looking at the supply chain and making it robust throughout.
Okay, thank you.
When? 5 years? I don't know.
These things happen very quickly. I recall from the explosion in lithium batteries that really only began in the UK in 2016 with the opening up of the market and the first tenders. And in less than 10 years, we've gone from 50 megawatts being a small 50 megawatts being considered to be a large scale battery to being 500 megawatts is talked about quite openly. We have but a few minutes left. I'm just going to sum up very briefly what my conclusions are from today. We've had 3 excellent presentations on quite different companies, each of which have got a particular angle. I think all of the speakers have shown us their enthusiasm for scaling up production and scaling up sales to meet a very fast and very growing demand. That's really good. We've heard different ways of doing it. Certainly, all the companies have got their technology under their control. Much of it is sourced within house and in their own capability. So their supply chains and their technology control is undoubted. We've talked a little bit about commercialization and the fact that there is a huge demand for energy storage. And we know from our own experience that energy storage is essential for infrastructure. We've talked about large scale in terms of large scale projects. We've left a big gap in that we've not talked about achieving volume of perhaps much smaller flow battery systems. Let's face it, to build a gigawatt of batteries, you could either build one large battery or you could build 1,000 much smaller batteries and still achieve a gigawatt, which has the same amount of storage. We've not really explored the paradigm of answering the layperson's question about batteries. Is it more important to have a megawatt or a megawatt hour? That's a whole new debate, and I think that the megawatt hours are going to be very, very crucial in the future. So with very little time left, we've got 10 seconds each if there's any final comments from our speakers before I finally wrap up. So let's do it in order. Nathan, any extras?
Sure. Been in the battery industry for more than 15 years. First lithium ion. Flow battery is really exciting. I think where we are today is where lithium ion was maybe 10 years ago. So
thank you. Tobias?
Yeah, and now the great goal is to get to where lithium-ion batteries are now, not within 10 years' time, but 5 years' time. So there's a lot of work ahead of us, and I think we are all ready and steady to accomplish what's needed.
Let's try and do it before 5 years. And Jean-Louis?
Yeah, I would second what my colleagues have said. Every industry, lithium-ion and others, went through this scaling up process before us. Let's be smart and observe what they've done, use the techniques that they've developed for, bulk production, service production, quality assurance, deploying in the field. All this doesn't need to be reinvented. It's there. People have done it before, and we're gonna implement that and grow fast.
Super, thank you very much. And David, next slide, please. Just a final reminder, if you can, you wish to take part as a presenter or author at the IFBF, now's a good chance to check out the website and put your paper in. Flow Batteries Europe will be working with the IFBF team, as you will expect, in order to create a very good program which will enable us to look not only at what is happening and what's coming around the corner in flow batteries, but also to explore what we've done and what our great achievements are. And for those of you that have been to IFBFs before, you'll know that much of the groundbreaking news about flow batteries has been talked about first at the IFBF. So that's a really good place to be. And next slide, David. And finally, just to remind you that we will send you the recording. Those of you that have got AI bots who've been trying to create notes from it, I hope you enjoy reading their transcripts and that it makes sense. I can assure you that I am live and you've not been seeing an AI invention. Not at the moment, that may come later. But can I thank Jesse and David for making the arrangements for this. Thank all our speakers for giving of their time to come and join with us. And can I thank you for joining us? And I do hope that if you're interested in flow batteries and you're in the flow battery industry, that you'll want to join us. So contact Jesse. You can see his email address there, or get to us straight from the website. We'd love to have you on board at Flow Batteries Europe, which is, I think, one of the definitive trade association for the flow battery industry. So with that, thank you all very much. Enjoy the rest of your day. If you're just waking up because you're in the Western Hemisphere, good luck. And if you're closing down because you're in Europe, well done, you've earned a rest. And if you're joining us from Asia, please sleep tight and look after yourselves. And we hope to see you again soon for another one of our webinars. Thank you very much. Goodbye.
Thank you.
Thank you. Bye-bye.
Goodbye. Thank you. Bye-bye.